let's carry on then from where we picked up. So if you haven't been following or you didn't watch the last video, we're going through this practical electronics book here. And this is the book that my lecturer actually recommends that I go through in order for me to get up to speed. Currently, I'm in second year and I'm studying instrumentation and control, which is a module that I'm really struggling on. And then also electronics and electrical principles too. I'm struggling big time on that. Both of them are around like AC, digital electronics, and yeah, basically things aren't going well for me at all. So what I've done is I'm going through this book now, working my way through it. I'm on page 84 at the moment. So we're just moving on to AC waveforms. And so the plan is to basically work my way through this book and hopefully get to a stage whereby I can understand what's going on in my lectures. So that's the plan. So we're reading through the book and taking notes as well. As you can see, I've got my iPad here in the corner. All right, so alternating current can take on many other useful wave shapes besides sinusoidal. Figure X shows a few common waveforms used in electronics. The square wave is vital to digital electronics, where the square wave, okay, yep, that's true, yeah, where states are either true or false. Triangular and ramp waveforms, sometimes called sawtooth, are especially useful in timing circuits. As we'll see later in the book, using Fourier analysis, you can create any desired shape or periodic waveform by adding a collection of sine waves together. Okay, so let's talk about, let's just write different waveforms. Right, so got the sine, you got the square. How has it done it? Square, triangle. Okay, that's not right. Yeah, best I can do for now. Triangle, triangle. My handwriting sucks. Sorry. And what if I missed out? Ramp. What's the difference between ramp and triangle? Okay, it ramps up, go straight down. Ramps up, go straight down. Then ramps up again. Okay, and then the good thing I can do with this iPad is I can make these a different color after the fact, which is nice. This is what I say to everyone. If you don't have an iPad, get one. It's just too good. I mean, this is obviously just notability. It's not the iPad itself, but yeah. Okay, and so what's this one? This is the ramp. Okay, and so we're saying that square waves are useful for or in digital electronics. Okay. An ideal sinusoidal voltage source will maintain its voltage across its terminals. Regardless of load. Okay. Okay, yeah. It will supply as much current as necessary to keep the voltage the same. Let's think about that. So we've got V equals IR. Right. So if the load once is using 300 ohms, and I should probably just use ones for now because it keeps it easy for the maths. But if you're using 1000 ohms and you had 10 amps of current and 10 volts, then V is equal to, let's just not even gonna work. V equals IR. So what am I doing here? 1000 ohms times, so 10 times 1000. This isn't gonna work, so it'd have to be, this is silly. Okay, let's change it. Let's use 1 amp. 1 amp. So 1 times 1000 would be 1000 volts. Oh yeah, 1000 volts. I don't even know what I'm trying to do here. This is a bit silly. Okay, let's scrap this. I think I understand. I don't, yeah. Clearly I don't properly understand, but I kind of get it. So, let's do this. Ideal sinusoidal voltage will voltage source, right? So we're talking, plus minus. So ideal sinusoidal voltage source will maintain its voltage across its terminals regardless of load. Okay, it will supply as much current as necessary to keep the voltage the same. Hopefully they give an example, because my example sucked. It will supply as much voltage as necessary. Okay. I just want to fit that last bit in. As necessary to keep, what was it? To keep the voltage the same. It would supply as much, no, not as much voltage, as much current. Yeah, current. It will supply as much current as necessary to keep the voltage the same. Okay, I'm kind of alright with that. Okay. An idle sinusoidal current source, on the other hand, will maintain its output current regardless of the load resistance. Hang on a minute, what does that mean? So the voltage source will just change, the current will change, but a current source will maintain its output current. It will just stay the same. So a voltage source is going to still, it is the same, isn't it? It's keeping the same voltage. It's just going to change how much current it pumps out. But the current source is going to keep the same amount of current that it pumps out. Is it going to change its voltage? Yeah, so it will. Okay. It will supply as much voltage as necessary to keep the current the same. Okay, got it. So opposite is true for ideal current source, which is this symbol. So we're saying so is it a sinusoidal current source? Yeah, sinusoidal current source will keep voltage the same. Sorry, we'll keep current the same. We'll keep current the same. Let's just put this into different. We'll keep. So we'll keep the current the same, but change voltage. But supply as much voltage as necessary. You can also create ideal sources of other waveforms. Don't know what you mean there. You mean square? Figure 2.83 shows schematic symbols for an AC voltage source, an AC current source, and a clock source used to generate square waves. Okay. So this is a clock source. In a laboratory, a function generator is a handy device that can be used to generate a wide variety of waveforms with varying amplitudes and frequencies. So function generators, I use one of these in digital electronics. Function generators I actually need to go back and study digital electronics again. Function generators can generate a wide variety of waveforms. Can generate different types of waveforms. Okay. A complete description of an AC voltage or current involves reference to three properties: amplitude, frequency, and phase. So amplitude is the same as magnitude. Okay. So describing an AC waveform. Okay, so you've got amplitude, frequency, and phase. This is a star, by the way, in case you can't. I know my drawing's not the best. Figure 2.84 shows the curve of a sinusoidal waveform or sine wave. It demonstrates the relationship of the voltage or current to relative positions of a circular rotation through one complete revolution of 360. Okay. It demonstrates the relationship of the voltage or current to relative positions of a circular rotation. So, shows the curve of a sinusoidal waveform or sine wave. It demonstrates the relationship of the voltage or current to relative positions of a circular rotation. Okay, I'm not really understanding this. So, shows the curve of a sinusoidal waveform. So, where's the curve? Where is it showing it? I don't get it. Okay, here. This bit. Okay, so what we're saying here is that this part here is relative. It demonstrates a relationship with the voltage or current. So let's just assume this is a voltage, right? Going up and down. To relative positions of a circular rotation through one complete revolution. Okay, so X is here, B is here, C is there at 180, A is there at 0, and D is down here at 270. Okay, so this is all relative. I kind of get that actually. So, for example, this point here would be what? This point here would be, so you got, I don't, so the rotation in time goes this way. Okay. So that means that this point here, sorry, this point here would be like here, right? And then this point here, close to C, would be over here. And here would match up with here, right? And then going back up towards 0 would be here, going back up towards 0. And right before 0 volts here would be here. I kind of get that actually. That actually makes sense. Okay. So let's try and draw this in a sort of way that I think this might just be the best way to draw it really. Okay, okay. I think I'll take a picture of it and then I'll draw onto it because this is quite a good. I think I'll get better than this. Okay. So we're dealing with, this is all to deal with amplitude, right? So amplitude. Okay. And then, so what we're saying here is that, let's say this point here is relative to here. So, okay, I kind of get it now. So this 90 degrees means that this here is 90 degrees. I get it now, I get it. Okay, let's pick another point. So this point here would be approaching 180 degrees, which would be over here, right? And let's do blue. So the midway point between C and D would be like, what, 200 degrees or something. So 2D would be like over here. And right next to 0 here would be, oops, would be here. That's actually quite cool. I get that. So as we're moving through time, so the wave's doing this, right? As we're moving through time. And so this whole part here counts. So this is one period, right? I think that might be wrong there. Maybe that's a cycle. I don't know. Maybe period or cycle. I don't know. I'm gonna go with let's say, okay. It says so it says it here, cycle. I don't know if that is also a period or not. I don't know. I'll leave that there for now. So this whole thing here is 360 degrees, or 2 pi. Does it have to radians as well? I don't know. 360 degrees is 2 pi radians. So would that be 360 degrees or 2 pi radians? I think so. And so this point here is 180 degrees or pi radians, right? And then this point here would be 90 degrees or pi divided by 2 radians, correct? Interesting, huh? That's cool. Okay, so how can I write that in words? What have they said here? They've said that shows the curve of sine wave. So the sine wave below the sine wave, it demonstrates the relationship of voltage to relative positions of a circular rotation through one complete revolution of 360 degrees. So positions below on sine wave relative to, what was it called? On sine wave with relative positions of a circular rotation through 360 of a circular rotation rotation of 360 degrees. Okay, I'm comfortable with that. So the magnitude of the voltage or current varies with the sine of the angle made. The magnitude of the voltage or current, okay, varies with the sine of the angle made by the circular movement. Huh? It varies with the sine of the angle. Okay, so where's magnitude? Magnitude's here, right? This is the magnitude. And this is the magnitude, right? Magnitude or amplitude, same thing, right? So the magnitude of the voltage or current varies with the sine of the angle made by the circular movement with respect to 0. Oh yeah, of course. Yeah, okay. I understand what you're saying. So you're saying that this position here, these two positions here have the same magnitude, and these two positions here have the same magnitude. Okay, I'm comfortable with that. So let's just copy this. Let's rub this out. So what we're saying here, is that these two, or how can I, let's put an X, that's a bit off actually, X and X, so same magnitude. So meaning that they're the same voltage, right? And then, for example, here and here, or here and here, same voltage and same voltage. Okay, I'm comfortable with that. So the magnitude of the voltage or current varies with the sine of the angle made by the circular movement with respect to the 0 point. The sine of 90 degrees is 1. Huh? The sine of 90 degrees is 1. I mean, this is where I may be struggling because of my weakness in trigonometry. But what does that mean? The sine of 90 degrees is 1. Let's get on your Google. The radius is 1. The sine of what? Why is sine taken to be 1? Sine 90 degrees taken to be 1. Okay. I'm giving this answer such that even a kid in 8th grade would be able to understand it. Thank you. Thank you. I appreciate the 8th grade explanations. Consider a right angle triangle because according to kids, trigonometry ratios are only defined for right angle triangles. That's true. If you make a right angle triangle such that theta is equal to 90 degrees, then the opposite side to theta, called the perpendicular side, or altitude. Okay. Why is it altitude? Okay, so if you make a right angle triangle such that theta is equal to 90 degrees, then the opposite side to theta, called the perpendicular side, would be like almost equal to the hypotenuse. Otherwise, the right angle triangle and theta won't be equal. Otherwise, okay, what's it talking about? Let's just draw it. You got a right angle triangle. Okay. So you got a right angle triangle. If you make a right angle triangle such that theta is equal to 90 degrees, then the opposite side. It wasn't supposed to be for an eighth grade kid. I'm struggling, me. Then the opposite side to theta, right? Okay, would be like almost equal to the hypotenuse. You what, mate? This is a downvote for me. This is not a good answer in my opinion. Anyways, and if the altitude, what's the altitude now? Why are you using these words? Stick to what people normally know. Anyways, and if the altitude would be almost equal to the hypotenuse, then due to Pythagoras' theorem, the base side adjacent to theta would be almost equal to 0. This way, our trigonometry ratio, sine is equal to perpendicular over hypotenuse. Sine is done by right? You use opposite over hypotenuse. Why is he talking about perpendicular? That's frustrating. Anyways, this way, our trigonometry ratios, sine is equal to perpendicular over hypotenuse is equal to 1, since both are almost equal. I think I did a video on this, but I forgot. Okay, anyways. You might have been taught that trigonometry functions only exist for right angle triangles. That's wrong. They are defined for any angle. You don't need a triangle. A much better visualization is to draw two orthogonal lines. What is that? The x and y axis. Okay. And a circle within its center of origin and radius 1. And radius 1. Okay. For any half line from the origin that makes an angle of 80 degrees. What? Okay, so None of this is making sense. Anyways, sine 90 does not equal 1. Sine 90 degrees equals 1. The unit's very important in trig functions because of the definition in higher math. These are all just math people that are like, this is all they do. So, mathematics hobbyists. So yeah, so they consider maths to be art, and it's all very serious. How dare you leave out the degree symbol? Get out of here, man. That's frustrating. Sine of an angle is defined by the ratio of the length of. I don't know if I'm gonna get anywhere here. Too many words, people. Too many words. Sine of an angle is defined by the ratio of the length of a side of the right angle triangle opposite to the angle to the length of the hypotenuse of the right angle triangle. Now, in a right angle triangle, we can clearly not have more than one right angle, because if we do, then we will no longer have a right angle triangle, as equal corresponding angles will instead give parallel lines. If you consider a right angle triangle, you will see that the hypotenuse is always the largest side, obviously. Thus, it would suffice to say that sine 89 degrees itself will give you a value close to 1. That was a big jump there, mate. Where, how, what? Okay, I'm an images type of guy, I am. Alright, this is okay. There we go. Image straight away. Unit circle. In school, you're probably taught about trigonometric functions in terms of the ratios of a right angle triangle. That's fine, but according to modern definition, trigonometric functions are defined according to the unit circle with radius 1 unit. Specifically, the sine of an angle is defined as the y-coordinate of the circle at that particular angle. The sine of an angle is defined as the y-coordinate, so here, of the circle at that particular angle, which is here. Okay, so if you want to know what sine 90 degrees is, check the y-coordinate when the angle is 90 degrees. Well, since the radius of the circle is 1, this implies that sine... Okay, fine. That makes sense because you've arbitrarily decided that circle with radius 1 unit. Although obviously, actually, that's not true because it has to be 1. The radius obviously has to be 1 in this, yeah, unit circle. That makes sense. Okay, I'm alright with that. So if you want to know what sine 90 degrees is, check the y coordinate. Okay, so you really don't have to prove that sine is 90 degrees, that sine 90 degrees is 1. It is actually defined like that. Man, maths is really not cool when you just have text like this, man. Look at that. That makes me want to cry. Okay. Sine x is equal to perpendicular over hypotenuse. Like, stick to the... I don't know if it's in Britain only, but I really prefer, opposite over hypotenuse. Anyways, perpendicular, as they say. Over hypotenuse, right? See above diagram. When angle is approaching to 90, okay, and hypotenuse will be of the same length. You what? When angle is approaching to 90 degrees perpendicular, angle is approaching to 90 degrees perpendicular. What do you mean? And hypotenuse will be of the same length. What? 80 degrees. So if you go to 90, no, I don't get it. Okay, so how did I get down this rabbit hole? So the sine of 90 degrees is 1. All right, so I believe you now. I feel like I should probably write that down and keep that in mind, actually. Let's just, let's go back to this guy's unit circle thing. So we got a circle. Oops, why is that ended up being a triangle? So we got a circle, and then you got a line down it. You got another line across it. Okay, 0, 360, 90, 180, and 270. Okay, so radius is equal to 1, right? And then so basically sine 90 degrees is equal to 1. So this is the unit circle. Okay, so according to modern definition, trigonometry functions are defined according to the unit circle. Specifically, the sine of an angle is defined as the y coordinate. Okay, so sine of angle is y coordinate. Sine of angle is y coordinate of the circle. Let me just make the circle a different color. There you go. Okay, and then you could say put this here. Move this all up. This is why I really, again, like I keep saying, I really like the iPad. Highly, 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 highly recommend it. So there's the y coordinate. And so since this is the radius, this bit here is equal to 1. Because it's equal to the radius. Alright, I'm comfortable with that. So where was we? The sine, that was a big long rabbit hole. The sine of 90 degrees is 1. Okay, so what are we talking about here? The magnitude of the voltage or current varies with the sine of the angle made by the circular movement with respect to the 0 point. The sine of 90 degrees is 1, which is the point of maximum current. Okay, yeah. The sine of 90 degrees is 1, which is the point of maximum current or voltage, yep. The sine of 270 degrees is minus 1, of course, yes. Which is the point of maximum reverse current. Okay. So we just define that as 1, basically, then, do we? Okay. So let me just take this again. Paste this here. Okay, so what are we saying? We're saying this bit here is 90 degrees or 1. And this bit here is 270 degrees or minus 1. Okay, and then this is also max voltage or current. And then this is also minimum, or not minimum, what is it? It's the maximum reverse. Voltage or current. You know, I in first year I was always looking at these waveforms, especially using when you look at on the oscilloscopes with multisim, and I'm just like, what is this? What does all of this even mean? I didn't get it at all. So it's nice. Like this is a good book. You know, there's still a fair bit of assumptions. Like, I mean, it's not too bad. Like, it's not really an assumption. They're actually just telling you, and you know, it's my inquisitive mind that's like, well, why? But it's good. It's nice. I mean, I like this book. You know, it's a good book. Okay, so which is the point of maximum current or voltage? The sine is the reverse. The sine of 45, what is 0.707? Um, okay. So the sine of 45 degrees is 0.707. So I should just be able to do that on my calculator and just prove that that's right, right? So sine, am I in radians? I am in radians. 60 degrees. Sine of 45 degrees. Nice. Okay, yeah. So it's 0.707, which happens to be, more than halfway up the sine wave. Okay, so let's pull all of this here. Let's do, what color do you have? We use orange. So sine of 45 degrees is equal to 0.707. So if this is 90 degrees, 40 degrees is halfway, right? Sorry, 45 degrees, I mean. 45 degrees is halfway. So what we're saying then is that this point here, even though this one here doesn't look as high up as that, but obviously, well, my drawing is probably not accurate at all. Anyways, so 45 degrees here, this is 0.707, right? And we're talking just in relation to this being 1. So this is actually starting to make sense now. If this point here is 12 volts, meaning that this point here is 12 volts, then this 45 degree. Okay, wait, okay. Let me work this out first and then I'm gonna write it down. So then this 45 degree angle point is 12 times 0.707. So this point here then is going to be 8.48 volts. That is sick. That's cool. So if you know the voltage at any one point in a sine wave, then you can obviously just work it out anywhere else. So once you know what the max voltage is, which obviously you always know, or I don't know if you always know, because actually there was when I was learning about op amps, it was getting saturated. This is what I'm saying. I was learning op amps without even knowing this stuff. So I didn't even understand what they were talking about when they were saying, "Oh yeah, it just gets cut off and saturated there." I was just that didn't make any sense to me. But now after reading this, I get it now. I get it. That's cool. Okay, so how can I put that into words? Okay, so I want to put it into words basically. Okay, so working out any voltage or current. I need to use some shorter hand things instead of having to write out so many words when writing notes. Okay, so 90 degrees is 1. And 1 represents max V or I, right? Then 270 is -1 and -1 represents reverse max of V or I. Okay, so 45 degrees. Wait, hang on a minute. So what would you do then? Would you do, I was just thinking that 45 degrees would be 0.5, but we just said that 45 degrees is 0.7. So would you always do, for example, like sine 200 is minus 0.34. So let's do that. So sine 200 is equal to minus 0.34. Okay. Then what would you do? How would you work? So what did we say? We said 0.7. So then you would, I don't know, what would you do? You would take 12 volts and you times it by minus 0.34, and that should give you the voltage level. So 12 times minus 0.34. So that would mean that you'd be at minus 4.08 volts. And then how does that relate to here? So we're saying 200. So this is 180. This is 270. So 200 would be probably about here. And so that would be minus 4 volts. And that would make this minus 12. That's about right as well, actually. Oh, yeah. Yeah. That's right, yeah. So sine 200 of 12 volts is minus 4.8 volts, which on the graph would be here. If you had 12 volts there and minus 12 volts there. Yeah, I'm alright with that. So let's just write out 45 is sine 45, which is equal to 0.707, which so to find voltage, I'm just trying to make my notes such that when I'm revising, if I look at this again in a week's time, let's say I don't do anything and I just look at this in a week's time, I'm still going to be able to understand it, which is a challenge. It is a challenge, a big challenge. So sine 45 is equal to 0.707. So to find voltage, you do max voltage multiplied by 0.707. So let's do, as an example, if we did let's do example 1, 12 volts max, sine 45 is 0.707. So 45 degrees is equal to 12 times 0.707, which we've already said was, what was it? 8.48 volts. 8.48 volts. And then we can just draw the little sine wave for that. Crap. Okay. I actually can't believe I'm doing this. I'm very impressed with myself. It's really fun to learn new things, especially to go from being completely confused to actually getting it. So then you get so 90 degrees is here. That's equal to 1. 45 degrees, and so that's equal to 0.707, which is here going to be 8.48, was it? 8.48 volts, and this being 12 volts, this being 0, and this being minus 12. Yeah, I'm right with that. And we can just call this one example 2. So what it is, when I go through and I study this again later on, I'll actually test myself just on this, and I'll say, okay, so if you got sine 45 and you got 12 volts, is that correct? What's funny is that I'm actually doing all of this, and I could be completely wrong. I could have just completely wasted the last 15 minutes. Why? Because I actually haven't even read on. So, okay, so I don't really understand this formula here. Frequency is equal to 1 over time. So frequency is equal to 1 over time. I don't really get that. And then voltage time is equal to voltage P. Where'd you get voltage P from? What's this max? Is voltage P max? Voltage P or IP? And then it's got PP and IPP. So voltage P and then sine 2 pi ft plus 0. I don't get that at all. So maybe, okay, I assume this part is for down here, I think. Right, well, as it stands there in terms of amplitude, I'm super comfortable with, I feel like I'm super comfortable with that. I actually feel a lot better, actually. Okay, so it only took me probably like an hour to do one paragraph. Okay, so let's move on to frequency. Frequency and period. So obviously these things aren't the same. I wonder why they grouped it together. Let's just do this on a new page. Okay, so a sinusoidal again. So a sine wave generated by a continuously rotating generator will generate an alternating current or voltage that will pass through many cycles over time. You can choose an arbitrary point on any one cycle and use it as a marker. Say, for example, the positive peak. Positive peak meaning here. Oh, okay, this is voltage peak or current peak. Got it. Got it. So, VP or IP is equal to peak voltage or current. Which, in case I forget, is I can't draw one now. That's not the best, but yeah. So that's either here or here, right? Okay. So the number of times per second that the current peaks in any 1 second is called the frequency. Okay, so number of times voltage or current peaks per second is called frequency. Is called frequency. That's a nice way of putting it. Instead of, there's the normal, well, once it's done one complete wave, that's its frequency. But I like that, the amount of times in a second that it peaks. I don't know if that's a proper definition, but yeah, this is what they say, so I'll take that. In any 1 second is called the frequency of the AC. It's called frequency or frequency of AC. Can I stick to frequency? I'll stick to frequency. In other words, frequency expresses the rate at which current cycles occur. So frequency is the rate. So why is this put current? Okay, current or voltage. IV cycles occur. The unit of frequency is cycles per second or hertz. So frequency unit is cycles per second or hertz. After Heinrich Hertz. The length of any cycle in units of time is the period of the cycle. Huh? The length of any cycle in units of time. Okay, so period has to actually do with seconds, meaning like if it was a very slow voltage and it took a whole minute, that would be one period. Period in seconds. Huh? Wait. The length of any circle and the length of any cycle in minutes of time is the period of the cycle. The length of any cycle in units of time. In units of time. So let's say seconds, right? So let's say you had. Oh, okay. So 60 hertz is one cycle. Sorry. Once. No. 60. Okay, wait. So you got 60 hertz is equal to 60 cycles per second, right? I get this whole one over stuff thing now. Ugh, I can't type. I can't write. Per second. Second. There you go. 60 cycles per second. So that means that you got 60 seconds. But yeah. So you're getting. How you get 1 over 60? Okay, so 60 cycles per second means that the frequency is 1 over 60. So if you had 100 hertz would mean that F is equal to 1 over 100. I get how you're going from 60 cycles per second to 1 over 60, but for whatever reason I can't explain it, so I'm not going to try to. Like, yeah, hopefully you get it. I mean, you're probably better at maths than I am, so you probably get it. All right, the length of any cycle in units of time is the period of the cycle is measured from two. Wait, what? The length of any cycle in units of time is the period of the cycle. Ugh. Okay. I'm gonna have to end this video soon because my brain's not understanding the English words. The length of any cycle in units of time is the period of the cycle. The length of any. I'm gonna have to read this 10 times. The length of any cycle in time. Sorry. The length of any cycle in units of time. The length of any cycle in units of time. Okay. Is a period of cycle as measured from two equivalence points of succeeding cycles. As met succeed. Go ahead. So why is it measured from two equivalent points in succeeding cycles? Okay. So one after the other, meaning. So okay. Yeah. Mathematically, the period is simply the inverse of the frequency. Yeah. I get that. So I was putting 60 hertz frequency is equal to 1 over 60 period. I don't get that. I don't know how I'd explain it, but okay, so I'm not really I can't really put this stuff into words here. But let's just write what they're saying. So they're saying frequency in hertz is equal to 1 over the period. Or 1 over time. So this capital T is time now. I thought the lowercase t was time. Okay, so let's put this into perspective. So if you had, I need an example. So you had 50 hertz, which means that literally means that you've got one sine wave and it's doing that 50 times per second. So it's doing that 50 times per second. And so what we're saying here is that the period of a 50 hertz sine wave is, we're not saying anything here yet. We're gonna write that down here. So we're gonna say that P is equal to, so period. Let's just write out for you. Period is equal to 1 over, this is a bit confusing for me. 1 over frequency, or 1 over F. So is equal to, so F is equal to 1 over T, and T is equal to 1 over F. I mean, obviously algebraically that makes sense, but so we've got, let's just think of the example. So we've got 50 Hertz sine wave, which means that it's oscillating 50 times per second. So the period is equal to 1 over the frequency. And we've said that the frequency is 50 Hertz. So the period is equal to 1 over 50 Hertz. So what does that mean? That means that the time in seconds. So the period in seconds is equal to 1 divided by 50. All right, fine. Yeah. I mean, mathematically I get that, but I don't understand the whole second thing. So for example, if I wanted to work out then how long it takes to do one oscillation, then you would do 1 divided by 50 on a 50 Hertz signal. So that would mean that okay, I get that. Yeah, I got it. So you get 1 oscillation, why did I say this word? There's no way to spell it. 1 oscillation every 0.02 seconds. Yeah. Okay. I'm comfortable with that. All right. Well, guys, I think I was actually given an example. Okay, so I'm going to pick up these examples from in the next video because my brain is now officially fried. So, yeah, as you can see, it takes me a while. It does take me a while to get through this, mostly because I've never studied this before. And not even anything close to it, really. I don't think I did this. If I did this in physics and maths, it was 10 years ago, so I certainly don't remember that. So yeah, if you watched all of this, thanks for watching, and in the next video I'm going to pick up from this page 86, and we'll do these examples. Hopefully it serves as a bit of a revision for me as well. Cool, guys, thanks, see you in the next one. Peace.